This is part 2 of section 6.3, Parametric Equations and Motion. In this part of the lesson, we are going to look at some ways you can make a parameterization of points, and also how do we work with simulating motion. And we're going to start with page 483, number 27. And for this set of exercises, the directions in the book say to find the parameterization for the curve. So for number 27, we are asked to find the line through the points and my points are -2, 5 and 4, 2. And we're going to call this point A and the second point, point B. So if we were to do this with vectors, it would look something like this. So if I were to just quickly sketch a little coordinate plane here, what I need, point A would be at like -2, 5. So it would be right here. Here's my point A and my origin here. And we'll call that actually point O. And then we also have 4, 2 would be right here. And that's my point B. So what we can do is we can draw these vectors. So we have vector OA right here. And then we have vector AB, which I'll draw in blue here. Now what I'm going to do is I'm going to extend that vector, and I'm going to put a point P on that vector. Now that point P could be up here, or I'll call that P prime, or it could be on this side of B. So we're going to do that, and then what we're going to do is we're going to draw a vector to that point. So we have our AB vector, so let me put an arrow on it, and we're extending that through there like that. And what we can do now is we can create this relationship. So we are moving this point P up and down line B in this way. So OP can be thought of as my vector OA plus some number T, a scalar, that's going to move that point P, times my vector AB. So when T is bigger than 1, it'll be beyond B, and when T is less than 1, it'll be to the left of B. So what we have then is we have -2, 5 is our components of vector OA plus some T times my vector AB. And I'll get that by doing my 4 minus the -2, so I get 6, and then 2 minus 5, which is -3. And so I am going to distribute that, and I get this for my next step. So I have a 6t and a -3t. So my final vector is going to be -2 plus 6t when I combine these two, and 5 minus 3t. And what I've done then is I've created my x of t, which will be the x component of the vector, and my y component of the vector will be my y, my parameterization in the y direction. Now that's what we're doing, okay? That's vector-wise, that's what we're doing. There is another way to look at this that might be a little easier. So let me rewrite the points here. So we have -2, 5, and we have 4, 2. So if I label each of these, I'll call this little a, little b, little c, little d. there's these relationships that you can use, and they are that x is equal to a plus t times c minus a. Those are all the x parts. A and c are the x parts. And y is equal to b plus t times d minus b. And you'll see how it's related to our final answer then. So substituting those in, my x is going to be a is negative 2 plus t times c minus a, which is 4 minus a negative 2. So we get x equals negative 2 plus 6t, which is exactly the same. Because if you notice, this part, whoops, sorry, I thought I hit the highlighter. This part is just creating my vector AB here. That's all I'm doing. And then here is the A right there with that. Okay? And then I can do the same thing with the Y. So then Y is going to equal my B, which is 5, plus t times d minus b, which is 2 minus 5. So I get y equals 5 minus 3t. Now, if you're a more visual person, you can do it the first way we did it here. If you like a formula, you can use this formula here. So either of those will work. All right, next question. Number 29 is slightly different because instead of a line, we want a line segment. So we can't have just a line. We're going to have endpoints. And so it tells us what the endpoints are. Our endpoints are 3, 4 and 6, negative 3. So using our little formulas from above, we have x equals a plus t times c minus a, and y equals b plus t times t minus b. So we get that x is going to equal 3 plus t times 6 minus 3. So we get that x is 3 plus 3t. And then y is going to equal 4 plus t times negative 3 minus 4. So we get, it looks like a 9 a little bit. We get negative 4 minus 7t. Okay, so that gives us our line. So how do we get our line segment, our endpoints? We have to put limits on what values t can be. That's what will stop the line from going past our endpoints. So here's what we want. We want it to stop at, for the x value, at 3 and 6. So you can take your x equation and you can set it equal to 3 and 6 separately. So if you take 3 plus 3t and set it equal to 3 and solve it, you're going to get 3t equals 0. You get t equals 0. And then if you do the same thing at the other endpoint, we want it to stop at 6. So when you solve this, you get 3t equals 3, so t equals 1. So it looks like for this equation, our t is going to be limited to 0 and 1. You could have done the same thing with the y values as well. You could have taken negative 4 minus 7t and set it equal to the y's. So set it equal to 4, or negative 4 minus 7t equals negative 3. And if I do this real quick, so if I add 4, I I get, oh, this should be a positive 4. I don't know why I put a negative 4 there. Here, I'm sorry. That should be a positive 4. When I do this, I get negative 7t equals 0, so t equals 0. And when I add this way, again, that should be a positive 4. I get negative 7t equals negative 7. So I get t equals 1. So there's your answer then. That's how you get your endpoints. So your x equation is here, your y equation, and you need those boundaries on t to get your endpoints. All right, one last part of this. We did one of these back in the beginning of the year as well, but the only difference was I gave you all the equations. Now you guys have the ability to write these equations for yourself. So Kevin hits a baseball. This is example 9 on page 480. There's going to be some different details on there if you want to look, but I'll try to get everything. So if you want to see it again from a different perspective, you can look on page 480. Kevin hits a baseball at 3 feet above the ground with an initial speed of 150 feet per second at an angle of 18 degrees with the horizontal. The question is, will the ball clear a 20-foot wall that is 400 feet away? Okay, so here's our picture. Let me just put an axis here. So Kevin's standing here, 3 feet is where the bat is. He hits the ball at an angle of 18 degrees. It's going to go up. It's going to come down. So the question is, if we have a wall here, let me draw that. It's a little too much of a slugger. If we have a wall out here, somewhere right here, that's 400 feet away, and it's 20 feet high, will this ball clear the fence? So we have to set up our x vector and our y vector for the distance. So the thing about the x vector, which is nice, is it's just one dimension, just going straight across. So you can use the idea that distance is going to equal the rate times the time. So in this case, x is going to equal, the rate is going to be 150 times the cosine of 18 degrees, because that's the x component of the vector that we started with right here. And you need the time in there. And what I'm going to do is, let me just move this over a little bit. Usually put the t in front of the cosine. It goes right in there. So I'm just going to rewrite that so it looks a little nicer. So you have 150 t times the cosine of 18. Now for the y direction, what you're going to have is the idea of motion affected by gravity. So you're going to use the equation, your initial distance plus your initial velocity times time minus the pull of gravity, the negative 16t squared. So we're going to fill that in, and we're going to get y equals, Kevin starts 3 feet above the ground, plus the initial velocity is going to be the y component of this vector, which is going to be 150, and I'm going to put the t in there, times the sine of 18 degrees, and then minus 16t squared. So there are the two equations for the ball. Now, how do we put the fence in? So those are the ball. So now the fence. The fence comes behind the idea of how long does it take to hit 400 feet. So if we know that x is going to equal 400 feet, we can set our x equation equal to it and solve for t. So we're going to divide both sides by 150 times the cosine of 18 degrees. And when we do that, we get that t equals 2.8 seconds. Okay, so we know that's how long it's going to take the ball to get there. So in order to draw the fence, we're going to need another set of parametric equations. The nice thing is that the x direction is easy. That's just going to be 400. The y direction, to get the 20 feet, what we're going to do now is we know that we want a y of 20 feet, and it's got to happen in the time. We're going to just like make this approximately go to 3 seconds times t, because if you think in this term, we want the 20 feet here, and then what we're going to do is take the time, multiply it, and then divide by how many seconds it takes to get there. So you can put, if you want to be really accurate, you can put 2.8 in there, but it's going to come out exactly right to be that. So if you would substitute the 2.8 in there, you'd get your 20 feet. All right, with the rounding. So all there is to do now is to put this in your graphing calculator. So I've already done that, and let me show you in Desmos how nice this can look. And I'll show you on the two graphing calculators as well. Okay, so in Desmos, how you enter parametric equations is you put them in as an ordered pair. So if you see, I have the 150t times cosine of 18, and then I have a comma, and then I have my y equation, and I've limited my t to what I want, the 0 to 3 seconds. One thing to caution you on is make sure you go over here to the tools. Let me move this over. I don't think you can see the tools. Let me make this the toolbar over here. Pull that up in the corner, and it defaults to radian. So if you see, it's not going to look like our nice curve. So make sure you change that to degrees. And then I put our fence equation in green, and you can see it makes a nice little fence there, and there's the arc of the ball, and the ball does not clear the fence. Okay, if you're doing this in the 84, so if you go, make sure you change it to parametric, it's the same thing. And make sure you look at the top and see that your calculator is in degrees, and there is my two equations, and then my window settings are the same. So I went from 0 to 3. I left the step alone, and I set my window for 500 for the X, so I knew I was past the 400, and my Y for 100. I knew he wouldn't hit it more than 100 feet in the air. And so when I do that, I get this graph, and so you can see the wall and the ball's curve, and you can see that the ball does not clear the fence, and then, or the wall. And then in the Inspire, same thing. You want to make sure that you have your calculator in degrees. Now be very careful if you're using the sketch pad grapher, or the scratch pad grapher, because that doesn't always change to degrees. It stays in radians. So you're going to get that weird curve. So I think it's always easier in the Inspire, especially if you're working with trig and you're using degrees, to use a graph page instead of using the scratch pad. And so there's my X1 and my Y1, and then the X2 and the Y2 didn't come up for some reason on the screen, so let me just pull that up. So there is that, and again you can see I put my T-step from 0 to 3, and you can see that it did not clear the wall. So we can go ahead and write that the ball did not clear the wall. And that is the end of the notes for section 6.3.